Okay. So okay, so we can let's start our operating system. Okay, so remember last week, so we talked about the fetch and execution state. In the stage, I think we spent some time talk about that. There's some question about the interrupt, and then so why not? So I think you're okay with the interrupt, right? So it's like because the boot screen interrupt, something's not expected, and the interrupt is like we already designed for some event happen, so we can just like let it get into. So it's an interrupt, and I found try looking for something can demonstrate they're going to have a first assignment soon, but not right now because more like the right now still some theory to write a C++ program to demonstrate, okay, for the like showing the what's the fetch and execute cycle. And right here, I would like to share one of the, I just found it right here. Okay. Just download it, enable cookies. Okay, so I just check it online. So there's some people they try to oh, I'm so sorry, it doesn't on. Sleeping mode. Second. And on on. Okay, okay. So it comes out. So we are stopped by right here about the fetch and execute stage. Remember we have the PC program counter, AC, and then the IR. And every time. And what I found is there's something to demonstrate. If you look at the screen right here, so it can maybe help you to have a better picture. Let's say if I have a option is adding. So right here, I'll execute. So in the beginning, we'll try to French. So this first add the program counter, and then we'll get the first location, 901. So in the IR, that means the instruction register, we will get the first digit is 9. And then the address register will go to 01. Okay. So, and then next. Go faster. And then right now, because they are IMP, we need to asking for input. If I want to input a number, let's say 24. Okay, so 24 will add to it, and then program counter increase. Okay, keep running, save it. Okay, so here's the loop. You see the program counter goes to 3, so we try to get the first input and save it. And you can see the register in the beginning, from the 0, the address 0, the instruction is 9, right? The address register 01. So 01, and then where we go is like go 01, and then next we are asking for one more input. Maybe I put it 10. Accumulate, and then 3, 4, 99. So you can see the address 34. So it's keep going. Let me stop. Okay, it's done. So right now you can see I input 24 and will be saved at 99. So because the instruction right here, so from the first one, so 99 is the address. Okay, so yeah, it goes slightly too fast, but right now the program counter goes to 6. So when you keep executing, so it really just like how just like asking for the sum, and then they will save the location 99 to here. Okay, so it's right here. It's the memory location. For better capture, I can share this one. Also, I'm looking for something that looks more fancy. Then I can share it so you can have a better understanding about the fetching cycle and then getting the information. Yeah, sure. I can reset it, and I can do the add. Right now, 1 really slow. So the program counter is 1. So we go to the first one to get the. Okay, when it's okay, we can follow it slowly. Okay, 901, the first address. So we increase the program counter. So the first digit is the instruction, and then the address register will be 01. That's what we get. And why not? Because we try to get the input. So this input is not in the register. So let's say I input the space. I will input number 7. I put enter. So once I get the input, so the AC, the accumulator saved the 7. Okay. Mine was really pretty slow.
So the 901 comes out of the 0.
Yes. So always like this one is simulating if our address begin from 0. So once our program counter always like adding 1 line for the stations. Well, we start the program counter 1, and then we go to the address like default. Address sometimes in really application we starting from 0, but somewhere else. But this one is just like try to have a program to simulate. So if we try to grab the instructions, so the first one like always remember the digits. Maybe we the 4-digit numbers we showing for the program counter last time in the PowerPoint right here. So we are showing it's the same. So it just make it to a 3-digit. So we just simulating the first, if the first one, suppose for the length, if you remember right here should be 16 bits. 16 bits with the opcode will be for the single digit, and then with the address is the registration, and then if the integer format will be right here. Okay, so let me make it. Yep.
On this computer.
Yeah.
How come it's not all zeros in this set?
Okay, so it's just only the simulation. Okay, so it just like begin with the default 01. So it try to get the first instruction position.
So
Is something confused?
say that again.
Okay, so because for this one we need to ask for the input first. Like here's the assembly language code. So first for our program counter we always increase by 1. Increase by 1 we have always the first address, like where should we load. If I go to here, when we the program counter we need to let's say begin with 300, it doesn't matter, or begins with 1. It doesn't matter. Just because we never actually most of the time we never begin with the program counter from 1.
In how it's, are we starting with 1 or 0?
From the problem right here is 300. Okay. And we always say, okay, so right here 300, we will get the 300, the first one. So we will grab the IR. So for the first one, what we get?
So
0.
931.
So because the program counter start with 0, right? So 0 was okay.
And that makes us go to the 0.
Yes. Okay, got you.
But
Okay.
put that number in. That's the instruction. Right?
Yeah, it's just the instruction there. Yeah. Okay.
RAM, and then it
Okay. In reality, actually, they are not really starting from 0. Really like depends on the status of current program counter. Actually, it may not be 0, but maybe 300 or like 400, 500, 1000. We never know. But just like for in lecture or teaching, just like give you a random number. Right here, I give you 300. So we just like jump into a certain
So
time slot.
So my question, I guess, is, so we're going to RAM and we're getting the instructions and we're taking them back to the CPU to execute them, right?
Yeah, going to.
So how do the instructions get on the RAM?
How getting the RAM? Okay.
You see what I'm asking?
Because back to this one, suppose it should get from the program counter. So program counter is like program counter will save which the next RAM we should go to. Okay. So program counter is the indicate, okay, where should I access to the RAM?
I understand.
Okay.
The program counter things. How does the information get on the RAM before the program gets to it?
Not yet. So that's why we need to have a program counter first. Get it?
So I think the program counter designates this is where our block that says this is where our instructions are stored. And so where you have the program counter, that's where you use the code.
Yeah, go to where to pull the content from the memory address. So the program counter is the saving the memory address. We should go next. Do you get this? Okay.
I'll ask. When you start up your program, it's going to get your code from storage. And then it'll put it into RAM. And so that's the first thing. Then what your program counter is what tells where in the RAM the code should go, right? Yes.
And actually program counter data they should have a list, right? Every time it give you a list. Maybe before the program counter execute, let's say your code start with 300. Maybe before it's like 299. 299 is doing something else. Okay, so we are doing something else, +1. So you say where to get the memory. So it's like really the program counter is telling you, okay, so next I should go to 300 to pull the instruction. What should I do? So what should I do is storing in this memory address. Do you think I answered your question?
So
this what
I complete instruction number 299 doing something else. Before I'll even think about starting number 300, I go and I load everything into RAM.
Before that, don't worry about that because that's what the OS system like taking other stuff. Why not we are focusing on this like the OS, like finish like doing other tasks like background service, everything. So why now we just like kicking into certain point. This point is like maybe you write on your own program, you're executing your own maybe there's a statement, so they load your statement, so they're running line by line. So we just like ignore what the previous is doing and just jump into this point. Okay, right now your program is starting at 300 and the program counter is like storing. Okay, so you need to grab the information from address 300. Do we get it?
And it gets put there because that's
Mhm.
what happened when we started.
Yes, yeah, and that's how the OS like more than that is like how to manage, because when you execute a program, and actually all of them they're putting in the sequence, right? So they will load to the PC.
When you start programming, the
Mhm.
first thing that the OS does is decide how it's going to that code. Basically, it's important. You're thinking why it was switched off already at the moment, but we're thinking after the program goes. It's about having after while we write the program, it's about how it goes through during the program. It knows that how the program works. Before the meeting something. So the registers are where the OS decided to put the instructions in the order. That's why it was really good.
Okay, so
We keep going.
okay, we shall. Okay, so I think some of you already know like what the program going. Okay, and it's the same right here. So we just starting point with the program counter 0, so it's 0, and then we press 1, and we go to address 0 to grab the instruction. So the first digit is the IR, so it's 9, and then the address register will be the last 2 digit 01, and we try to get the input, and the input will be saved in the AC. So this is how the things work. And keep running. So right here, the program counter after we get the input. So like always in the cycle, we always increase the program counter. So we'll add it +1. And because the address register is 01, so we say, okay, so we are going to address 01 to fetch the content. Let me fetch cycle. It's right here. So we'll get the 3 and 99. Slow down. Okay. Because in the assembly code is I execute one by one. So all those codes will be like showing, okay, am I getting input, or I save it, or I store it to the address. So when I 799, right here, 99 is the address of it, instruction 3. So we are like store it. And right here, if you remember, 2, okay, so 2 right here. Okay, so it may be this it shows that different instruction to adding, so it's not same as what we're doing. And right now the value was saved to 99. Okay, and keep. Okay, the input right here. Okay, okay. So the right now 99 is the address, and the next cycle the program counter should be 2. And this one is the previous that after we execute 3 and then go to address 99. Okay. And right here, and then we will get getting the second number 2, and then grab it 9 instruction and 01. Okay, and then we ask for one more input. Okay, so one more input, maybe I'll put it maybe 10. Slow down. Okay, so once I put the 10, it go to the AC. AC will save the value. Okay, I slow down. So program counter still will +1, and then we are instruction going to 3 to grab it. So right now we are going to grab the address run. The value in the memory is 199, and the first digit is the instruction, and then we have the address. So it's slowly into here, 199, and then next one, 199 is the address of the last one. So we are going to there. Okay, it's loading. Yeah. Okay. Instruction Y. Because right now the AC is the second input, we save it, and then we go to the AMU. And then the fourth instruction, okay, so we're getting it. Program counter already +1. We try to fetch the content. Okay, so when the instruction is 902. So 9 is the instruction, so same address. Okay, so we have a 17. So we save the output, and 5. Program counter already saved. So what now what need to do is that because the PC is 5, so we go to address to fetch like what we're going to do.
I'm assuming that 5 is 0.
Okay, yeah. So it will clean the instruction will be 0, and then the address value also is 0. Okay, so it's done for this part. So basically, it demonstrates it's a whole cycle, like how we increase the program counter, and then how we load in the memory. It doesn't not only the data itself, but it also including what's the instruction, what's going to do, and then which address location they should go to fetch it. So you can see right here, 99 is about the address, and then sometimes we have the input. We save it in the AC. It's a temporary, and then if we need to put it to the register, so we put 1 and then save to 199. So it will save to the register. So how it simulate is the whole the program counter. And right here, I think we already saved. So this is a overall review. We skip the review. And we last time we stopped by the interrupt right here. So we say we interrupt is we try to add it in case there's some higher priority event happens. So we need to like detect it. So basically interrupt is like we can detect those issues and try to let it interrupt so we can like escape first instead of like we can get into the cutting the queue, get into it. Okay. And here's the example we have last time. And when we try to do like for the hardware, simple like if processing. So if we have some like device controller or other system hardware, okay, issue. Most of the time if we get the mic input or like keyboard or mouse, they can be all interrupt. Okay, some physical. And then the processor will finish execution of current instruction. Also, it will try to like signal an acknowledgement of an interrupt. So in case, so we detect it's an interrupt. Then they will push the PS stub and then the program counter onto a control stack. Sometimes like it called a control stack. We have the stack like saving the program counter, so we know okay. Because we ask like program counters like telling us like which next memory address which go. But when we have an interrupt, then the CPU need to take care of it. So after we finish handle it, then we need to go back to the stack and go maybe go back to the process. Or sometimes if based on the interrupt, we cannot keep on executing, then we will change the PC. So we cannot keep on like +1 or go to the one on the stack, but we need to jump on another status. And in the software layer, we go back. Okay, so right now we will save the reminder of the process state of information. And then that time the process really interrupt. And after interrupt, we will restore the process state information. So we will go back to finish the rest of it. So we say that all this will be under control, you know, like we will know the interrupt is going to happen, like it comes in. And if something happen out of this flow, then it causes the blue screen. There will be something like happen out of expectation. It's right here. And if we look at here, if we need to like change for an interrupt, so let's say we have the program counter, suppose like normally it's the n+1. And then we have the general register and then the stack pointer. The location you can see at T-1, maybe something right here. And maybe some in certain moment, we have the interrupt route start from here, Y, and then the length is L. Interrupt, and then we have like this law is like for the user program. Once we have the interrupt, it comes in, we execute. And because right here, you can see Y plus L, the Y is right here. In the beginning, because we know it's like N plus 1 Y. Okay, so we'll execute the interrupt. So once the interrupt, it happened, the program counter right now will be +1. So it's the PC still like adding 1 on it. Okay, it's good. Just let you know right here. Okay, so we will execute, return, and after we come back, and we will go back to the rest to finish it. And we have we have one single interrupt, then it could be possible we have multiple. It's possible, right? So okay. So how are you going to interrupt? Is we always say add them because in the memory, so we like the Y plus L plus 1. So suppose like in the beginning, so we will also have save it to the stack. So when the program counter is right here, we save the stack, and then the new interrupt comes in, we will handle it. If in case I keep going new interrupt, save it, the program counter to the stack. You know the stack and the queue. Okay, so the reason why we need to using stack instead of queue, have you think about? Why we need to, if we have interrupt? Yes, yeah, it's like first in, last out. Okay, yeah. Yes, correct. So right there you can see like right here the picture is like Y plus L plus 1. So suppose I we'll try to finish the rest. Okay. And when we have more, then we will try to pass the rest. Okay. And that's how we can like keep on getting a next interrupt, handle and come back. Okay. So right now we'll after I talk about how the CPU can the process, and then we'll move on. Okay, so basically to know how the memory hierarchy. In the major constraint in the memory always about the amount, speed and expense. So most of the time the memory we need to like keep it up with the processor. So because they always say working together, we always like try to fetch the content from the memory to your CPU. After your CPU like do some like calculation math, we need to save it, put it back to memory. And most of the time when we need to think about the cost of the memory, we need to be like more reasonable. Just why for the like old school, maybe the RAM may be less than one gigabyte, but I think at least right now, if you get the new computer, begin with like 8 gigabyte or 16 gigabyte or 32, right? So have you ever checked how many memory are you using right now? Do you know how you check? Even you didn't, maybe you just open a PDF. Can you show like how many percentage have you occupied? Yes, yeah, yes, yeah. Yeah, task manager, or you can go to, yeah.
I think I'm using 9.9 out of my 15.8 gigabytes.
Okay, 9.9. So you can see what kind I can, okay, maybe you open the Chrome, and what else? You can go to your task right here. Task manager, I think it's right here. I think it's the active right here. Okay, my activity monitor is on my, is my memory. Okay, so it's pretty pretty a lot, because mine have a 32 gigabyte, and you see, even I don't really use a lot, but I didn't really open. The memory is the memory we are talking about is the RAM. Is the RAM, yeah. So it's the RAM is the memory we are using right now. So if we have 32 gigabyte, because for the RAM we need to have a header. So if like in the reality, actually the memory you can use is less than what you can actually use. Like the least, if you see it's 32, have you ever used the USB, like when you plug in, you say I bought a 32 gigabyte USB, but when you look at the available storage right now, it should be always less than that. Okay, so because all those are memory, they use part of it as a header. Those header will be showing the architecture of this USB file. How can you access it? Sometime when you have a crash, or you cannot, because the header file will be like corrupt, so you cannot access to it. When we consider actually the memory size going bigger, also because the why now lots of application, even your OS like loading it, they will occupy part of your memory. Before maybe like 4 gigabyte would be enough. 8 gigabyte, even older than me, like maybe 8 gigabyte is really a lot. But why now we say 32? I will already use 17. Actually, I didn't really, I just like open my Zoom, a PDF, and that's it. All these like the amount, and if we want to have a because the RAM just more likely, you just imagine it's your table, like your Vertex. So you can put more stuff on your table, then you are easy to access. But if you want to easy looking for your stuff, then you need to have a bigger table. Okay, so how big can be? It's impossible to get thing in infinity size, right? So always a limitation. And also when you're getting a higher high amount of the like more storage space, the price also always goes up. Do you know how because you most of them I think you are using laptop. Anybody try to embed your own desktop or no? Like how much for getting your own? Okay. Do you know how much for one maybe 116 gigabytes of RAM? No, I said okay. Let me look at it. I'm not really like updated, but I can check. For the 16 gigabytes, for the regular, okay, so it's almost like $30 per one. Okay, yeah, so it's like it would be 16 gigabytes. Yeah, so if you want to go something like 32, they have 216 would be like 50 something. So I say this price is pretty acceptable, because like for the RAM price really depends on the market needs. Sometimes it goes up higher than that. Okay, yeah, sometimes it drops back. Okay, and just like basic information, we know the memory is helping, the RAM is helping to have a faster access, because we need to load it from the SSD to the memory to the CPU. And if we are using the old time, we are using the hard drive. Do you know what's the, I think it's the 3.5 inches, the really big one. I think I think it's this and important. So that one is the really is the bottleneck for the processing, because we have to load the information. Because in CPU, we can finish, actually in the whole architecture of a computer, CPU always like can process the most fastest one. So we can finish within the nanosecond, we can finish like so many instructions. But the most slow one is the hard drive. But why not I change to SSD, solid state drive? So the speed is getting like closer. Because it's kind of like more like it's the not volatile memory. So it can help the speed like transferring. Also like because another thing is much more physically, we'll talk about the bus size, but here's the change it. It's still the same when we change to SSD. Higher, maybe if you get 1 terabyte SSD, I remember it's more than 500. And all this, we have the limitation, and because this one is kind of like old school, is like about the two, they say the 2-level memory, because they have different type of memory. So when we have the basically when for 2-level memory, it, like just a portion. So when we have access from level 1, the time will be higher, and then it drops when we have involved with a less fraction. But for this one, we are not, because it changed. We changed the hard drive, so it's kind of like outdated, but just in the in the syllabus. And the principle of the locality is like the memory referred to the by the processor 10 to the cost, and data is organized so that the percentage of the access of each success safely low level is sustainable less than that level above. So, and then can be applied across more than 2 level. So maybe slightly complicated, but just like remember, this one is for the memory access. Always like when we access to it from the lower speed to I say SSD is the lower speed, it will affect the processing time. So it's good enough. But right now we are this one is not the updated one, so we can know a little bit. And also we are kind of like have a cache, so it's invisible to the OS. So even for the memory, the CPU, the OS system, they don't know exactly like what's the cache inside. So it's integrated with the drive to handle it. And with other memory, so this was the memory hardware, and the processor must access the memory at least once per instruction cycle. So you know at least one, because you see the program counter. If you remember the program counter, we need to always like go to the address and fetch it. So it's just what we know. Okay. And then also in the cache, we always like contain a copy of the portion of the main memory. And if the processor first check the cache is not fine, then we will go to, okay, so we'll try to read a block of memory and then go to cache. Do you know the difference? Like, do you know what's a cache memory right here? Okay, actually, we always the cache is like buffer. Even though we are like the CPU reading the data from the memory, actually it's still very slow. Okay, just like what I said, CPU to memory first level is they're close, but still like processor can finish within like one instruction within 9 nanoseconds. Okay, but memory still takes some time. If we go more like one level down to the SSD, it takes more time. So in with every level, we try to add up some cache. Those cache will be like frequently used or like previous use. So we will save in the cache. Those cache, the speed is like closer to the upper level. So if we have the cache for the memory between memory and the SSD, so the cache will be closer. So when the memory try to retrieve the data from the SSD, let's see if I can find it from the cache. If no, I really load it from the SSD. Here's the same. CPU also try to get the data from the memory, but we are not always go to a memory. First, we check the cache. Okay, do I still have the data? If we still have it, then we just load it from the cache. If no, then we need to load it from the memory. And then we'll save to cache load. Okay. So it's the called locality. Okay. And here's the picture right here. And maybe just here's a kind of like overall picture right here is like CPU. Then we need to transfer like from the, if we omit the caching, getting from the main memory. Okay. maybe you're thinking, okay, when a CPU getting information like data from the main memory thing, okay, it's really fast. Actually, like really based on the really architecture, like that's why CPU is more expensive than memory. We always try to add up some cache to do remember we have the level L1, L2 cache in the, I think in the computer architecture, right? You know that? Okay.
Yeah, the L1 is one that's right next to each core.
Okay, yeah, right next to, yeah, available. Yes, that's how we the reason why we're adding those like caching, because it's like adding more buffer, so we can save your time retrieve from those other memory. But I say memory because main memory is that RAM, another memory can be the storage. So here's the one more.
So each of those. All except for the CPU.
If you look at the hardware infrastructure, all those RAM always like built nearby the CPU. Or like in the CPU. Yeah. So they are not the those cache are not built or like embedded with the slower one. Okay. Yeah.
So is that like temporal data in like browsers and stuff that is like in hardware?
Those cache, they are also like kind of hardware, but it's like the speed, like processing is like kind of like faster or closer speed with the higher closer to the CPU. Okay, because all those like actually it's a physical hardware for the caching. We just ignore because we have some caching is like as a software or virtual like in the memory. Okay, but we don't talk about this part because this one is more like physical hard drive. Actually, they are part of it. It's still really expensive, like adding more like two layers or 3 layers. And you can see like in which every layer, if we increase the size of the cache, also it will increase the cost. Yeah, to like building the hardware.
Increase the effectiveness by increasing the size of the cache.
If we increase the cache size, actually we can increase the effectiveness. Because you say decrease, right?
So I figured if the cache size is bigger, you have to deal with more.
No, no.
There's a lot of we're not going to get that. Then the processor is just better.
Bill, I think you're slightly confused about like you feel like more stuff, so it is slower, right?
Yeah, that's what I was saying.
How about others?
Yeah, but let's say that again.
Okay, because he said okay, because we try to add the cache, like it's a more like hardware. It's like when we increase the cache, it would decrease the performance, right? But it spend more time because you need to grab the stuff. So that's how he think about that. But how about others' opinion?
I would say the opposite.
Okay, suppose like if I increase the cache, we will increase the performance, right? How about others? Which way? I think you think it's increase, right?
So as you increase the cache, you have to do it's generally better as far as you have. There's a certain point where you have too much.
Okay. First, I think about the hardware. Why we are adding cache?
To reduce the distance that you have to fetch data.
Also, yeah, distance. Not only distance, but also the speed, like the access speed of the cache is faster than memory. Okay, so if I can, yeah, if somebody.
So the cache. Okay. Main memory in this picture. That is not RAM, right?
It's RAM. It's RAM. Yeah, main memory, we call main memory, it's RAM. Okay, very clear. Okay, we always another name is called main memory. Okay.
divide our RAM into sections. For example, the top one is level 1.
No. Level 1, level 2 caching is right here is like really physically have an extra
You have extra.
It's not you can imagine it's the RAM but have a faster speed. Kind of like the speed is closer to CPU. So from the leftmost, you can see the CPU have a fastest processing speed, access speed.
Oh, it's built into the motherboard?
Sometimes they build with the CPU. They will like cut part of the CPU. So like with it like inside, yeah. If you look at the architecture of the CPU.
I think the purpose of the cache is to, you take what's on your RAM and then you copy it onto the cache. So
Yes.
It's just closer to the CPU. So it's easier and faster to get to.
Yes, okay, this is the purpose why we have a cache. Okay, so then back to your question. If I have a like bigger cache, will we affect the speed like decrease or increase? Yes. Yeah, safe. That means because in one of the level is that CPU is the fastest, like always like finish the process really quick. And main memory, if compared with the main memory is slow. If the memory compared to the SSD, even the old school, like old time, we are using hard drive, and it's even way slower. Okay, it's the slowest. That means like if I finish the task, but I have to waiting for reading the data or I waiting for the information to send it. So it's wasting time. So we say, okay, can we add some cache or buffer? If there's something like I will retrieve regularly, then I can increase the speed. Also, those cache will be have a like closer speed to the like high performance. So the cache like most of the time, if you look at the architecture of the CPU, they will just say L1 and L2 always they stick to the CPUs. They have ALU and math, and also they will divide L1 and L2. Most of the time, maybe not the old school one will be we have the L1 and L2, but one now maybe they'll add the L3. So there are 3 layers for cache. So Bill, when you say why don't we use more L1 level 1 cache? It's closest, right? Can we replace like change all the level 1 to 3, change to 1? Can we do it in this way? Then we need to back to the speed amount money. Yeah, because when we are increasing, like if we want to use really high level, like really fast cache, that means the price goes up. Yeah, so that's why they need to like cost down. So they need to think always like the fastest and like high performance cache have keep it as a minimum amount. Okay, and that's how it works.
So is the cache used by every program, or is it just certain programs that things are?
It's all the program loading. Okay, so here the cache is more like physically you can use it. So when the OS comes out, and then it will send all the instruction to the CPU, right? So CPU, let's say if I'm looking for the address CO1, get the data. So first I will try to find if this pieces of data is it stored in cache. If yes, I just grab it. So all the time you just assume it's like big old 1 like this. Just 1 second, grab it. So like if I have something right here in front of my desk. So if I want to, let me try to find something in my memory, but let me see the cache. I have it, I just grab it, I can use it. If no, then I need to go to the main memory. Okay, and when we decide like 3 levels, so because this one is right in front of me, so I can grab it's really small desk, right? Because it's really expensive, so the cost goes up. So I need to have a slightly cheaper. Okay, I have a level 2 caching. So if I cannot find it right here, I go to level 2. Okay, slightly slower, but it's still faster than just directly access to the main memory. And then level 2, maybe we decide 3 level, then I will go to level 3. I will change it. If no, then I really go to my main memory to get it. So get it. So it's like apply for all the instructions. Okay. So that's like more like hardware, like how we use it, all those resources. Okay. And in the cache, you see that it's slightly like shorter than it. So we have the block, we have the test 0 to 1C-1. And then with the block length with the keyword, so we save in the cache. And then in the main memory is like way bigger. So 16 gigabytes or like 32 gigabytes of memory address start from 0 to and 2 to power n-1, right? So we know this the same size, and then we just like have a cache value. And here's the showing how we doing the cache reading operation. So we will receive the address, the RA from the CPU. So is it this block containing RA in the cache? So we check the cache. Okay, so the normal way how we do is that, okay, this RA will have a word and then we just deliver to the CPU. So it's done, simple. If no, that means like, okay, in the cache, it doesn't contain the data what we need. So we need to access the main memory for the block which containing the RA, they're saying. And then allocate the cache slot for the main memory block. Okay. And one time in meanwhile, first the load the main memory block into the cache. Also deliver the RA word to the CPU. So that's why how we save. Then there's a question. If the cache, then means right here, because the cache always they have a less size than main memory. Okay. So when it's like occupied, I say it's full. When I have a new address, if I need to get something. So are we going to how are we going to do?
You're saying the cache is full and you need to get something that's not the cache. You import the next level up in cache. Yeah.
So actually the same is no. So is there no? I just go to the main memory.
Oh,
Okay, the same way. Okay, so it's sound like I'm tricking you. So it's same operation. So because the mechanism is doing it this way. So does it exist in the RA? Okay, in the cache. Okay, so no. Now I'll go to main memory, get it, and then save it. Just replace it, and that's it. Okay. Because once we right here, because once we retrieve like access the data from the main memory, so we will do it like two main process. First is like load it to the cache, so we will replace one of it, and another one in the meanwhile we will deliver the RA. That means like the cache and then to the CPU. Okay, same time, so we save it. So next time if we need to get those same pieces of data, then we just like get it from the cache if we need it again. Okay.
Oh, so we decide whether or not we redo the.
Actually most actually there's suppose there should be have different mechanism like you need to predict how often are we using, or like if for the new cache if there's some pieces of data is new, so which one should we replace? Actually we hopefully we can discuss like later in the like, because like in the cache we have limited size, right? So if we have like from 0 to C-1, then which one should you replace? Suppose the last use or the first one below, like the oldest, so we can discuss. This one is about like how to manage the cache. Okay. And here's a basically okay. And next, if we have the multiple core, well, I think it's really common, right? So this one is like one CPU. And if we have multiple cores, so we will combine actually different cores have all the components. And actually, you're just thinking we put all the processes together. So they are allocated. So there's we need to check if in certain level the software that allow actually say, okay, those program is supporting multi-core. If they're supporting multi-core, that means okay, we can divide those like block statements like into different parts. So I can assign to okay CPU 1, CPU 2 to handle it. If some of them they didn't really when they doing implementation, they didn't think about doing multi-core. But suppose right now already we have really popular. So all the application they do consider like allowed to doing this. But when they first come out from the single core to like 2 cores, they may not able to support to do it. Okay. And also those multiple core can do in like L2 or like something L3, but most of time will be stop at L2 because when we're adding more cache, it's getting more expensive. In the market, sometimes when it's cheaper, so it only have like 2 levels of the cache. And here, maybe some of them you can see a label you're using i7. Okay, so in the i7, most of the time we come with the 4 cores, so 0 to 3, and then you can see the size of the L3. Oh, not the L. Oh, maybe I can start with L3. So you can see the architecture is like L3 is the slowest, but it can get the 8 megabytes. But when we get closer, like upper, so L2, 250, and L1, 32. And right here is called a DDR3 memory container. One now should be DDR4. I'm not really following the hardware, but suppose the latest one now still like we are still not yet have a DDR5 or comes out, but we still.
DDR5 is just out, but it's very super good. Like it's super good. Because if you get an AM5 chip, the only thing to drive DDR5.
Okay, DDR5. Okay. Yeah. Also, one thing is but this one is more like hardware computer architecture because in different like 3, 4, 5 comes out because they need to change their motherboard. DDR5 you cannot use the DDR4 motherboard. So based on the market, but when the manufacturer always like getting a new standard like the DDR5, so we are keep fading out the previous one. You can see why the size is dropped a lot. Mainly it's about the cost amount. If you say, okay, can I change the L1 to 8 megabyte? Then you cannot like using use the same price buying the i7 core. These are things.
So all 4 cores share the same L3?
Yeah, they will share the L3. Okay. We are not really studying how to like exactly manage because this one is more going to deeper level how the CPU. Also, actually CPU is a really complicated architecture. So, but we are not we are just showing like how it works. So it's called the symmetric multi-processor SMP. So all the like standalone computer system, we have a following characteristics. So two or more like similar processor, comparable. Okay, and capability processors share the same main memory. So we know the main memory is the RAM, and are like interconnected by the bus and other internal connection scheme. So you heard a lot the bus. If you okay, right here, okay, the graph. So when we talk about the bus, actually is the right here. So all these like the bus. So the width, the bandwidth of the bus also affects the transmission. And also the processor will share access to the IO devices, and all the processors can perform the same function. So system is controlled by integrated OS. So you see all this hardware will be controlled by the OS. So we in all the processors, if we look at the picture, all the processors we have like their own. So right here, the level 1 is like really inside the processor, and then we have maybe the L2 will be outside. That means like on the motherboard, but it's close to the CPU, and they are connected by the system bus. So if you curious like what's the system, but they have to on the motherboard. So on the motherboard they have some maybe you not really see, have you seen the lines on the motherboard, and then later after we plug in, if we connect to the SSD, nowadays I don't think, long time ago we have the CD-ROM or like the USB, so they have another cable on this. So the IO system, and we have the main memory. So that's how it connect. And so just like before we move on, because of the time, so I just cover the part of the direct memory access. So we know what's the direct memory access and how it works. What is the IO access? So it's possible it's like program the IO, interrupt driven IO, and then direct memory access. For the program IO, so when the process encounter the IO, it executes the instruction by issuing the command to IO modules. So the IO modules provide the request action and set the result bits. It does not interrupt the processor. And processor must take some active role in determine when the IO is complete. And processor periodically check the status of the IO modules. So it's called program. We talk about the interrupt, right? So this one is like not really interrupt. It's just like the CPU need to be active. I have to check. Do we have an input? No. Then I know you. If I come back and check it, if you have some input, I will take it. And interrupt different IO. So it will be do you know all this like IO? We have the drive. So have you tried to like plug in USB or maybe your mouse, keyboard? Windows, I think from you right click the computer property, you will see all those like the devices, IO devices. So in the old time, as when you see the transformation of the hard drive, before if you have let's say if a network adapter card, then you need to install like input it or install it the driver. Otherwise you cannot use it. So all those drive, they will include the what's like handle with the IO. Yeah. Some of them just like program IO, so it's just like waiting in list, let it check for input. But some is like about the interrupt. So it's like when it have something detected, then it will send it to a CPU. So we can kick off the interrupt, like let it get in. Okay. And once you finish the request service, then we can send it to the processor. And the one we mentioned about the direct memory access. So when we have the large volume of data to be moved, so we are better use the DMA. So it's the direct memory access. So both the IO setup and the transfer of the data controlled by the DMA and IO modules. That means the driver. Often the DMA use or need a special processor to control the transfer and negotiate usage of system bus. Direct memory address just like transferring a big bulk of the information. When sometimes when we like copying data from drive to drive, so we just like directly access. Maybe from A drive, sometimes you would divide your hard drive to, have you seen you have C drive, right? Only C drive. Somebody will divide your own like D drive or like other drive. If you're copying for those like mainly the IO, the drive will help you to handle it. So actually it doesn't require the CPU to process any information. So it is like copy from a D drive to E drive. Okay, so here's a kind of like 3 types of the memory access. Okay, and so far will be for today. We talk about the processor, main memory, and the IO modules. Okay, and that's it for today.
Yes, so
Mm-hmm.
whenever I,
Mm-hmm.
so you were talking about the ISMS.
Uh-huh.
And